This is Mrs. Westmoreland, and this is Introduction to the Mole. From last semester, we learned that the relative atomic mass, the numbers on the periodic table, is a weighted average of all the naturally occurring isotopes of an element. And the standard upon which 1 AMU is based for relative atomic mass is 1/12 the mass of carbon-12. For molecules which are covalently bonded, we use the term relative molecular mass. That's because covalently bonded substances usually exist as small numbers of atoms joined together by covalent bonds as discrete molecules, real pieces of matter with just small numbers of atoms, like the water molecule in the picture. For ionic bonds, we use the term relative formula mass when we talk about the mass of an ionic compound. That's because there isn't a real piece of matter represented by the chemical formula NaCl, for example. NaCl, or sodium chloride, exists as a giant crystal of repeating positive and negative charge, like the one in the picture. So the formula just represents the whole number ratio of positive to negative charge, and we call that the formula unit, and so the mass is called the formula mass. Both formula mass and molecular mass can be calculated as the sums of the atomic masses of all the elements in the chemical formula. Here are the steps for finding formula or molecular mass. First, write a correct chemical formula for the compound. This is why that skill has to be learned in the first semester and continue to practice all through the rest of your PreAP Chemistry year. Then we look up the atomic mass for each element from the periodic table and round it to a whole number. This is just to make the math easier. There are a couple of exceptions that aren't really close enough to whole numbers for rounding, so we're going to keep chlorine to 35.5 and copper to 63.5, but everything else can be rounded to a whole number. Then we're going to multiply the rounded atomic masses by subscripts and add all the masses of the elements together. Here's an example. We're finding the formula mass of calcium phosphate. So calcium phosphate is an ionic compound, and therefore we call it the formula mass. Calcium has a mass of 40 on the periodic table, pretty close to 40, so we round it to 40, and there are 3 atoms of it, so we multiply by 3. The 2 outside the parentheses applies both to the phosphorus and the oxygen of the phosphate ion, so we round the mass of phosphorus to 31 and multiply by 2. We round the mass of oxygen to a whole number of 16, and we multiply by 8, since the 2 distributes and multiplies the 4. Then we add all those together to get a value of 310. Here's a couple examples for you to try. Pause the video while you write the correct chemical formula and add up the masses. Here's the answers that you should have gotten for the previous slide. So ammonium sulfate is an ionic compound. Need to balance out the charges and have the correct formulas of both ions, and then add up all the masses of the nitrogen, hydrogen, sulfur, and oxygen. So 2 nitrogens plus 8 hydrogens plus 1 sulfur plus 4 oxygens all adds up to 132. Then in the next compound, dichlorine heptoxide, this is covalent with the prefixes. We use the prefixes to make our subscripts, so Cl2O7, and then from the periodic table we multiply 2 times 35.5, remember chlorine is not rounded to a whole number, and 7 times 16, and add those together to get 183. Now, you may be wondering why I didn't include any units on those numbers. Well, That's because the same numbers can be used to calculate the mass for a single molecule or for a mole of molecules. For a single molecule, we would use the unit AMU. For a mole of molecules, we would use the units grams per mole. Why can we use the same unit to talk about a single molecule and a mole of molecules? That's because we're talking about relative masses. Here's an analogy. A golf ball weighs 17 times more than a ping pong ball. So, 10 golf balls would be 17 times heavier than 10 ping pong balls. 1,000 golf balls would be 17 times heavier than 1,000 ping pong balls. The relative mass is the same no matter how many you have. The same is true for atoms and molecules and formula units. The masses on the periodic table are relative masses. One carbon atom weighs 12 times more than one hydrogen atom. So, 10 carbon atoms weigh 12 times more than 10 hydrogen atoms. And 1,000 carbon atoms weighs 12 times more than 1,000 hydrogen atoms. So a mole of carbon atoms weighs 12 times more than a mole of hydrogen atoms. So when we talk about the mass of a mole of something, it's called the molar mass. And molar mass tells us that 12 grams of carbon 12 contains 6.02 times 10 to the 23rd atoms of carbon 12. So that number, 6.02 times 10 to the 23rd, is known as Avogadro's number or Avogadro's constant. And 1 mole of any substance contains that many 6.02 times 10 to the 23rd representative particles. A mole of carbon contains 6.02 times 10 to the 23rd atoms of carbon. A mole of copper contains 6.02 times 10 to the 23rd atoms of copper. A mole of pencils contains 6.02 times 10 to the 23rd pencils. So a mole is like a dozen. It's a way of counting things. But it's a way of counting things that are really, really small. So the molar mass of any substance is calculated using the same numbers as the relative atomic mass or molecular mass or formula mass, but instead we measure it in grams per mole. So now we've kind of talked about 3 different ways of measuring matter. We can count the representative particles, which can be atoms or molecules or formula units. We can use mass, and that's measured in grams. And we'll talk about a 3rd way, which is volume, which is mostly measured in liters for gases. The method the scientist uses, or the unit we decide to measure in, is usually chosen because it's easier, or we need that particular type of information. But once a measurement has been made, then we can convert between the units. So here are some of the different ways that we can connect the measurements that we make in the real world to moles. So 1 mole of a compound is equal to the molar mass in grams that we add up from the periodic table. 1 mole of an element is equal to Avogadro's number of atoms. 1 mole of a compound is equal to Avogadro's number of representative particles. And 1 mole of a gas is equal to 22.4 liters. So the mole is the link between all of those other units of measurements. Notice that the compound is called Avogadro's number of representative particles. That's because we use different words to describe the representative particle of covalently bonded versus ionically bonded substances. We use molecule for covalent and formula unit for ionic. for the same reason that I discussed when we talked about the difference between molecular mass and formula mass. This diagram will allow us to use dimensional analysis to make conversions between grams and moles, moles and grams, particles and moles, moles and particles, liters and moles and liters, or even connect from mass all the way over to particles. Please watch the next video to see me working some example problems that follow in this slideshow.